Now let's go to site amplification, which is another important topic, and a very, very important topic, actually, I should say, when we talk about the geotechnical earthquake engineering. If you look into any book of geotechnical earthquake engineering, a lot of portion of that book will be devoted to the site amplification. And why it is so? You can see in this picture, the buildings which are on bedrock are experiencing lesser amplitude of vibration, which the building which are on shallower soil, having shallow bedrock, are having little more shaking, but the soils which are having at deeper soil are having higher magnitude of higher intensity of shaking. Okay, why this is happening? And McMurdo, who is in 1824, he himself, he also reported this. It is one of the first written account of this effect. He quoted that buildings situated on rock were not by any means so much affected as those whose foundations did not reach to the bottom of the soil. In 1819 earthquake in Kutch, India. Okay, this is the example from India, and one of the first examples of one of the first written account of local side effect, that the buildings which are on bedrock are not affected much by the earthquake, but the buildings which are on the soil, soft soil, are affected much more. Okay, and this has been seen a lot of time in different earthquakes, even in Gujarat earthquake. Okay, in Ahmedabad, where the lot of damage occurred to the buildings which are near to the river, which are lying over the sand. Okay, so site amplification occurs. There are different kinds of reasons for this, and one is the geometry and material properties of the subsurface material, the soil, the property of the material, the site topography. If it is a concave topography or a convex topography, means topography. If it is a hill or a basin or a valley, for hills amplify the motion. Hills amplify the motion due to focusing. The valleys de-amplify the motion by scattering the waves away. Topography and the characteristic of input motion. If input motion is of the similar frequency which is of the ground, then resonance may occur. You must have studied this, the effect of resonance. Very famous example, which we studied when we are kids, small, in 11th 12th classes, that march past is not allowed by the army over the bridge. Okay, parade is not allowed over a bridge. Why? Because frequency of the parade, marching people may coincide with the resonate with the frequency of the bridge, and if it happens, the amplitude of the vibration will increase and bridge may get damaged. The same thing can happen with soil. If soil has a similar frequency which are of the input motion, means the earthquake motion, then the amplification will be much higher. So amplification influences all the properties of the ground motion. That is the amplitude of the motion. It may increase the amplitude of the motion. It can change the frequency of the motion, and it can also alter the duration of the motion. To the softer sides, the duration, we will see that the duration increases. So major seismic damage was from this we can understand that the major seismic damage is controlled by local geology. If we are on a hilltop, then we may experience higher magnitude, higher intensity of motion. And if we are on a valley, we may experience lower intensity of motion. For example, if you have visited Delhi, then if you are near the parliament or places nearby the parliament, you may experience lesser intensity of motion because it is on rock. But if you are near the Noida, there you will feel higher intensity of motion because there is the deep soil. The similar thing were also experienced in the Kathmandu earthquake also in recently in 2015. So each soil responds differently when subjected to ground motion. This is expected because each soil means there are stiff sand, soft soils. Okay, different kinds of soils. What kind of soil we are, how stiff it is, how strong it is, that defines how well it can amplify the motion. Okay, and that is the whole topic needs to be studied in detail, and that is a very interesting topic. These are the local side effects. Topography, so what are the general parameters which control the local side effects? That is topography, I told you, basin and valleys, hilltops. Then geomorphology, like if it is rock, if it is soil, if it is soft soil. Okay, ground water table also sometimes affect the this local side effects, and the bedrock motion, bedrock depth. The deeper the bedrock, thicker the soil layer. Okay, and higher the amplifications may occur. But if it is too deep, the Ganga Yamuna basin, the Doab region in India, where the rock is around at 3 kilometers at some places. Okay, Doab region is the region between Ganga and Yamuna. If and there, this is the depth of the soil layer is almost 3 kilometers at some places. So at these regions, at these locations, this may also cause de-amplification. Okay, of the waves. So better depth of also affect local side effects. When we say local side effect, we mean that changing the motion. As I told you earlier, that a person sitting inside the room will hear less volume of the bomb explosion than a person who is close by to the who is outside the room. That room is making changes to the sound. That making changes to the sound. In similar way, the soil modifies the motion. Okay. Now, how the site amplification? If you remember the concepts of reflection, what happens is as soon as the earthquake waves strikes the junction of hard soil or hard rock to the soft soil, the velocity of wave decreases. As soon as the velocity of wave decreases, as it is entering into the softer medium, the velocity of the motion decreases. And as soon as the velocity of the wave decreases, conserve the energy. The energy is transferred to the particle, and as the energy is transferred to the particle, causes the increase in amplitude of ground shaking. Another reason, this is one reason of increase in the amplitude of ground shaking. There is another reason is due to the layering the wave inside the layer, and by moving to and fro in the same layer, the motion increases, the motion amplifies. Okay, so the gist of the amplification, how amplification occurs when waves enter from rocky media to a softer media. When we say site amplification, what we mean is the motion which is at soil site divided by the motion. Here we have a record at soil site, and here we have a record at soil site. And when we divide the motion at soil site by the motion of at rock site, we get the amplification function, how much there is amplification. And when we talk about the amplification, we talk about the amplification at particular frequencies, not in time domain. Okay, this record is in time domain, means this record shows me what are the amplitudes at different time. And if you do the Fourier transform of this record, you will get something like this, which shows what are the amplitudes at different frequencies. Okay, and when we divide these amplitudes, Fourier amplitudes of two sites, one is from rock side and another is from soil side, we can get amplification function or the transfer function of these sites, that how much the soil side is modifying the motion. That there are two ways of doing this. One way is the rock side can at the surface, another is the rock side can be at the bottom of the same soil side. And this gives us a very good picture of how much this soil layer is modifying the motion. This modification is shown by the transfer function shown in the bottom, and a very theoretical picturization of this amplification function is shown in the left, where the highest peak occurs at 0.6651 hertz, and the amplification is 9. So that means that the frequency, which is the motion at the frequency which is at 0.6651 hertz, is amplified by 9 times. Okay, the soil side amplified the motion at 0.6651 hertz by 9 times. Okay, the other peaks shows the higher modes of the same thing. The first frequency shows the first mode of the system, and the second and third peaks also shows the higher modes of the amplification function of the system. Now, there is a small video from educational website IRIS I have downloaded to show you the effect of different kinds of waves affect the buildings, and how the different kinds of soil affect the buildings. Okay, these the buildings which are on the left side are on soft soil. The buildings which are on right side, the yellow building, they are in soft soil. Left buildings are on hard rock or stiff soil. The buildings are on right side are on soft soil. The building which is very close to the water, is on soft soil and the building is and the soil is saturated. And as we discussed, when the soil is saturated and sudden shaking occurs, the chances of liquefaction are there because of loss of the shear strength of the soil by increase in pore water pressure. So let's see the video. There are three, as I told you, that P waves are the compression waves. The motion of the wave is in the direction of the wave propagation. S wave are perpendicular to the direction of propagation, and surface waves cause a rolling effect. A rolling effect. Both Rayleigh and Love waves cause a rolling effect to the ground. Okay. Now let's see how the buildings are there. As I told you, that the left building, that pink one is on solid rock. Okay, white one is on poorly consolidated sediment. This yellow and the yellow and the brown one are on water saturated sand and mud. So let's see how the different kinds of waves. Now earthquake strikes, and this red one is the P wave, and we can see the P waves just moves the buildings up and down. Why? Because it's compressional waves and it has a low magnitude, and it causes the motion in the direction of the propagation of wave. So wave was moving upward, that's why the motion is up and down. Now see how the S wave will affect. Now S wave will come. See, S wave is moving sideways. The buildings are moved sideways, and the buildings which were on the soft soil were affected much more than the buildings which are on solid bedrock. Now comes the surface waves. You can see from this video also that P wave and S wave, as they are body waves, they come from the inside of Earth, but the surface waves are coming over the surface, and due to the rolling effect, they cause much more damage. Even still, they don't cause much damage to the solid bed, the buildings on solid bedrock. Okay, now let's see what happens to the building in water saturated sand and mud. Okay, so all the four buildings were made of had the similar design, but the first building is not damaged. Second building was damaged a little bit, but the third and fourth building are completely damaged, and there is a liquefaction at the fourth building. That is due to the saturation. The soil was saturated. There are two case studies I am discussing here. This is the Michoacan earthquake 1985 from Mexico City. Mexico City was 350 kilometers from the epicenter still, and the whole city can be divided into three zones. The one is the foothill zone, another is the transition zone, and the third is lake zone. Lake zone is the zone where the thick deposit of soft soil is there, and foothill zone is the zone where the hills are ending, and the transition zone is between the soft soil and the hill. The foothill zone has a rocky site, and it was found that the foothill zone, the damage was concentrated at the lake zone, mostly at the lake zone. Even not even the transition zone, not even the foothill zone. The highest damage occurred at the lake zone, and the buildings which were damaged, most of the buildings which were damaged are in the range of 5 to 20 stories. And why that happened is the due to the resonance, because this kind of because the due to the soft soil, the frequency content of the earthquake motion was changed, and it came to very low. Okay, it came to very low, and it resonated with the buildings which are high rise. That's why it is a very common perception that on soft soil, in soft soil, you should not make high rise buildings. If you are making, you must take better precautions. Small buildings are good. Low rise buildings are good for soft soil sites, because the low rise buildings will have lower frequency, no, sorry, higher frequency, and they will not resonate with the earthquake motion. Okay, so this what happened at Michoacan earthquake, where the most of the damage was concentrated in the lake zone. In the same city, the buildings which are on foothill were not damaged, and but the buildings which were on Lake Zone and are 5 to 20 stories were damaged severely. Similarly, there is another earthquake which is San Francisco Bay Area earthquake. During the localized effects were observed in San Francisco Bay Area, and this is the Loma Prieta earthquake 1989, where the intensity is normally given in the MMI scale, okay, which provides the experience of the people. So the MMI, the intensity at the epicenter region was just 7, but the intensity at the San Francisco area, which is 100 kilometers from epicenter, was 9. So means what this means is someone who is just near to the bomb has he heard lesser voice of the bomb to the person who is farther away from the bomb. How could it be possible? It is possible because that person who is farther away from the bomb is hearing some kind of device, having some kind of device which is amplifying the voice. So this here, the San Francisco Bay Area soil was amplified the motion, and the intensity was increased by 2 points, and we had a MMI scale 9 intensity at San Francisco Bay Area, which was 100 kilometers from the epicenter. And there are 2 examples of Yerba Buena Island and Treasure Island, which were, one is a rock outcrop, another is the soil, and it was found that the defensive oscillations there was quite high. One is it's almost 3 times at the San Francisco Bay mud area, which is at the soil side, in comparison to the rock outcrop, where it was only 0.6 G, 0.06 G, and 0.03 G, and at the soil side it was 0.16 G and 0.11 G. So it was almost 3 to 4 times at the soil side. Okay, and that is quite high. Okay, so there are different methodologies used to be studied, which are required to evaluate the local side effects, and this is a topic of research. These methods are used in the in the research, and whenever if some of you are doing PhD or research in this area, you must be using these methods. Even if you are not doing that, you will use these methods. Or if you are even designing the buildings, you must be very familiar with at least one method, which is the empirical method, that is estimation of VS30, and the 1D ground response analysis. The estimation of VS30 is the average shear wave velocity of the top 30 meter of soil. Okay, that means the speed of the shear wave velocity, the secondary wave, the travel speed of the average travel speed of the shear waves, the secondary waves of the top 30 meter of soil. That gives a very good picture of the soil stiffness, the shear strength of the soil of the top 30 meter. And this VS30 again can provide us a good measure of amplification. There are lots of empirical formulas. Even our codes, even IS code also gives different response spectra for calculation of loads for different kind of soil: soft soil, hard soil, rock. Okay, so when we talk about soft soil, hard soil, rock, in Indian code, the classification is based on SPT and values only. But in all the foreign codes, VS30 is a very common term which is used to classify if it is a soft soil, if it is a rock, or this is one very common method which you must encounter whenever you are designing any building using Indian or any other code. Okay, and there are theoretical methods, which is 1D ground response analysis. 1D ground response analysis is very common for doing the analysis of amplification, how the amplification occurs, or even liquefaction studies. Also, this kind of study, ground response analysis, is done. The most common software for this is Shake 2000. Okay, developed in Berkeley. Berkeley. Okay, so these are the different kinds of methods. Most of these methods are, but this V30 and 1D are very common to be used in industry also. From this, what we can conclude from this whole thing, we can conclude that for design of earthquake resilient structure, knowledge of underlying soil strata is of utmost importance. I'm just reading what is there in the slide, because that is completely saying what we discussed by this time. Okay, because the underlying soil may modify the earthquake motion, but to a great extent, and that's why we must know how the underlying soil strata will behave when earthquake occurs, and how the structure over that will behave due to that modified motion. So This understanding is very important, and what you have for your career means why you study this. If you see this picture, I have shown Kashmir, I have shown Himachal Pradesh, I have shown Uttarakhand, only these three things I have shown. And if you move west, you will be having Uttar Pradesh, you will be having Bihar, Sikkim, Assam, and many other states. And here you will have Punjab and Haryana and Delhi. If you have seen the demography of India, you must be knowing that almost more than 50% of the population is residing in this zone, which is affected by this, which will be affected by any earthquake occurring in this region. Even although the earthquake occurred in Kathmandu doesn't cause much damage in India, but the earthquake, which is known as Nepal Bihar earthquake in 1930s, caused a lot of damage in India, in Bihar. Similarly, the earthquake in 1905 in Kangra, that is in Himachal Pradesh, caused a huge damage, and at that time more than 10,000 deaths were reported in Kangra. Okay. Similarly, lots of damage, lots of casualties occurred in Assam when in the earthquakes in 1950s. Okay, so the loss of construction is going on in these places, and whenever someone is constructing something, you must be he must be well aware of the site conditions, and the site conditions to know the effect of earthquake. You must be having the understanding of earthquake engineering, the geotechnical earthquake engineering. Okay, so that's why this is very important for your career. Also, this subject, the understanding of this subject is very important for your career. From the perspective of research, this is very important because from the perspective of research, a lot of studies are going on for microzonation. As I told you that the response spectra of India is shown divided in just three zones, that is soft soil, rock, and hard soil. That is due to the fact that we don't have much VS30 data. Okay, we don't have much VS30 data. We don't have done much work on that area, and a lot of work need to be done. So and these days, lots of people are working on this area in different research institutes and academic institutes. So there are lots of possibilities in research as well as in industry if you have an understanding of this subject.